today. I had to travel very far from the second floor. It's many flights of stairs. So I'm going to tell you about low memory convex optimization. So first, why should we be interested in low memory convex optimization? So to motivate this, I want to tell you a little bit about my old computer. So I almost gave the talk on this old computer because my new computer, anyway, it was a long story, terrible. But my old computer, so it was a fine computer. Actually, most things about it worked fine. And it had 16 gigabytes of RAM. I bought it in 2013, and at the time it was the most RAM that I could get on a MacBook. And for me, it's important to have a computer with a lot of RAM because I like to process large data sets, and the easiest thing to do is you load them all in memory, right? And then you just don't have to think about it anymore. They're all in memory, you can do very fast manipulations, right? And I like to solve large optimization problems, and it's nice if you can fit everything in memory, you can remember what's going on, you don't waste time checking out solutions you've already checked out, things like that. So it's much nicer if the thing fits in memory. So I thought, great, well, now it's 2018, I've got a big grant, I can buy a new computer, right, with more memory. That was my hope. So I went on the Apple website to buy a new computer, and I like a 13-inch model because my hands are relatively small. And the maximum memory I could buy was 16 gigabytes. And I thought, well, that's lame, right? It's 5 years later, right? Well, and there's no more memory.
Maybe you should be looking outside of just laptops.
That would have been a reasonable thing to do, yes. Okay, so no, there's,
I did buy a machine in 2012 with 128 gigabytes of RAM.
Yeah, it's going off the screen a little bit.
Could you hold on your lap?
Yeah, if you do mirroring, it usually.
Yeah, no, I got it mirroring.
Weird.
Yeah, that's a great idea. Actually, sometimes if you full screen it and then full screen. This is I shouldn't have bought a new Mac, right? That was the problem. All the problem with this Mac technology. Speaking of working for Obama, when I worked for Obama, they gave me a laptop associated with this, which was not a Mac. And at the end of the time that I worked for him, I finished up a couple of projects after I went back to Stanford. And after the campaign, I tried to look into how I could return my laptop to the Obama campaign. And it was kind of confusing because the campaign itself had dissolved, right? It didn't exist anymore. And so like the assets of the campaign actually, like they couldn't belong to the campaign, which did not exist. It was not a company anymore. So I tried to figure out who they belonged to. In fact, they were the personal property of Barack Hussein Obama. And so I realized I had Obama's laptop. But I didn't know how to give it to him, right? Because I tried to give Obama a laptop, I probably wouldn't have worked anyway. So, old laptops. Great. So the hope was that even if RAM is smaller, at least maybe it's cheaper. I can, if I got a bigger computer, maybe. But no, it's not cheaper either. These are very expensive computers. Okay, once again, Apple. Okay, I should look beyond Apple, but actually, even if you look beyond Apple, there's been a problem. So this is Moore's law for RAM. So this is the cost per megabyte, dollars per megabyte of RAM over time. And you can see that things got off to a rocky start at the beginning. It was sort of flattish for a while. Then it started going down pretty nicely. So this is the curve that you would associate with Moore's law, right? So a linear decrease on a log scale, right? So these were the good old days, and now even these kind of been, it's a little jumpy, but flat-ish since maybe 2013, okay? Which coincidentally is when I bought my previous computer. So it doesn't seem like this is just a phenomenon restricted to Macs, right? This is like a real thing. For a long time, algorithms are able to sort of ride on the back of hardware, which is getting better and better and better and better. And now we don't know how we're going to make hardware better, smaller, cheaper. And actually memory is the first thing that died. Yes?
It's useful to see that, but we might also point out that within the last 5 years,
Yes.
there are speed benchmarks that continue to improve.
Yes, that's right. This is Moore's law for
Size, yeah.
This is for dollars per megabyte, right? And other metrics have continued to improve. But basically all of the Moore's law metrics, no one knows how they're going to. No one knows what the next technology is, like for 10 10 years out. So basically all of them are probably dead after 10 years, but it's interesting that memory is the first one. It's the first part of Moore's law to fall. So it's worth thinking about how we can design algorithms that use less memory.
But that's not true for all memory, that's just for RAM, right?
Yeah, and the hard disk we're okay. You know, if you want to store things for a long amount of time, well, like, you should use DNA storage maybe. If you want to really fit things in there. Okay, but that's also good for optimization. Where you want fast access. Okay. So on the one hand, this is bad for people who want to run things on large data sets, but it's good for people who want to design algorithms because it presents a new set of algorithmic challenges. Okay, so why should we care about low memory algorithms? Well, Moore's law is running out, and it's also nice that low memory algorithms are often fast, right? If you don't look at a lot of things, then maybe you'll spend less time doing whatever you're doing. And why convex optimization? Really, there's some mathematical reasons, right? There's a robust convergence theory. There's elegant analysis. If you want beautiful optimization, I'd say it's the place to go. And maybe it's the right thing to understand before you understand anything more complicated. So we're gonna focus on convex problems in this talk. Okay. So I'm gonna both of the algorithms I'm going to talk about in this talk are based on the conditional gradient method, which is a classical method developed by Frank Wolfe for the particular case of quadratic optimization problems with linear constraints and quadratic objectives, and then extended by Levitin and Polyak to more general convex problems, and they called it the conditional gradient method. And there's an interesting correlation between times when Moore's law for memory has broken down and interest in the conditional gradient method. Okay, so between 1956 and 1966, those are, well, one is off the charts, one is right here in the sort of flattish period, right? And then there's renewed interest around 2010, 2013, right? So when we start hitting the second plateau. And I don't think that's an accident. Okay, so this is a method that's particularly good for low memory optimization. So let me give you an example. So suppose that we're trying to minimize a smooth function g. And we've got some parameter alpha, it's a real number. And we want an iterative method to solve this problem. We want to minimize g subject to a one-norm constraint on alpha. So the sum of the actual values of the coefficients of w is bounded by alpha. So iterative methods, they solve some kind of subproblems inside. So you want the subproblems, you're going to do a lot of them, you want them to be easy and fast. Essentially, there are two main kinds of subproblems that people look at. One is projection onto the constraint set. So in this case, projection onto the one-norm ball. And here, you can do it, but it's kind of complicated. It's so complicated, there's a paper about it. Okay. Whereas linear optimization of the one-norm ball is actually easy. So if I want to minimize a linear function given by x, so the inner product between x and w, over the one-norm ball, what's the answer to that? I'm going to draw a picture. Okay. This is the one-norm ball. Here are my coordinate axes. Okay. This is the set of points where the one-norm of w is less than or equal to, let's say it's 1. So this value is 1, that value is 1. Suppose I want to minimize the linear function x. Let's say I'm going to draw negative x. This is negative x. Okay. What's the solution? Right. So I want to find a point inside this set with minimum inner product with negative x. It's down here. Right? So if I draw the level sets of this curve, right, of this linear function, right, the maximum level set is the one that hits right at the corner. Okay? So what's interesting to notice about that is that that's a sparse, that point is sparse, right? It has a non-zero y value, but a 0x coordinate. Okay, so it's a particularly simple point, which might be useful if I want to use a low memory algorithm, right? I don't need to use a lot of numbers to describe that point, right? I just say which coordinate axis is that point non-zero on, right? And that's this representation. I can say it's the ith unit vector, right? The unit vector in the ith direction times alpha to scale this norm ball of the alpha. Okay. So the conditional gradient method builds on this insight. And it's useful for problems where linear optimization over whatever shape you have is an easy problem to solve. Here's where it would be nice if my clicker worked, but we'll just have to deal with it as is. Here's how it works. Imagine I'm minimizing some smooth function g over the polytope p. So here's my polytope. I'm going to represent it by its vertices, v1 through v5. And let's suppose my initial iterate w0 is at v1. The first thing I do is I compute the gradient of my function g at w0, and I look in the negative g direction, the negative gradient direction. Okay. I'm going to look for the point that the point in my polytope that maximizes the inner product of the negative gradient. Okay. And that's here it's v3. My next iterate is going to be somewhere on the line between v1 and v3. Okay. And different methods of Frank Wolfe do something different for finding a point on that line. You could do line search, or you can use a fixed step size. They get the same convergence rate, but if you do more fancy things, it converges faster in practice. Okay, but I've got W1 somewhere on this line. Now I do the same thing. I compute the gradient at W1. I look in the negative gradient direction. I find the vertex that maximizes the inner product of the negative gradient, V4, okay, and I step in that direction. Okay. I keep going on like this. Now, one thing that's kind of interesting to notice is that a given iterate, right, at every iteration, I take my previous iterate and I add some vertex, right? And so my new point is a convex combination of the previous point and the new vertex. That means I can represent this point as a convex combination of the set of vertices that I visited. Okay? And in particular, the number of vertices that I need in that representation is never more than the number of iterations. Okay? So if I stop the algorithm after not too many iterations, I get a sparse solution. Right? If these vertices are sparse, or if they're otherwise structured, right? I get something that's sparse in whatever the structure of these vertices is. Okay. So what's wrong with the conditional gradient method? Well, number one, it's slow. It's quite slow. And that's a problem because the complexity of the iterate grows with the number of iterations, right? If the number of iterations you were going to take wasn't very large, then that's fine. But if you have to take a large number of iterations, that's pretty annoying. I'm going to show you two methods that we developed for different problem settings that allow you to run something like the conditional gradient method using substantially less memory. So the first is the limited memory Kelley's method, which starts out actually attacking a problem that looks very different. So let me tell you about this problem. This is a problem from submodular optimization. We assume there's some ground set of vertices, what we call vertices, 1 through n, and we're going to identify subsets of this set of vertices with Boolean vectors, right? So there's going to be a 1 in a given entry if that vertex is in the set and a 0 otherwise. We're going to call a set function that goes from these Boolean vectors to the real values, is submodular. Suppose you take a set A that's inside a set B, contained in a set B. If we add the vertex B to A, and we compare that to the value if we just look at the value to A, we get more than if we add the same vertex to B and subtract the value of B. Okay? So this is like the property of diminishing marginal returns. Right? Adding a vertex to a smaller set gets you more than adding the same vertex to a larger set. Submodularity captures diminishing marginal returns. It's also worth noting that linear functions are well, they're both sub and supermodular. They're just modular. And we're going to define W of A. So if W is a vector, W evaluated on the set A is just the sum of the coefficient of the entries of W for coordinates in A. Okay, so let me give you an example of a submodular function. Suppose we're looking at the cover function. Okay. Here the sets are going to represent, the ground set represents these circles, okay? And the function is going to compute the area covered by all the circles that we've selected. Okay? So if let's set the purple circles on the left, these are going to be the set A, and the green circle is the circle V. So when we look at the value of A union V minus f of A, well, that's exactly the area of this green circle. On the right, I'm going to look at a set of green circles B that contains set A. right? And if I add this green circle to that set, the addition to the area is less. Okay, so the area function satisfies the requirement for submodularity. This is a modular function. Okay. Okay. I'm going to do a little bit more math, but you actually don't need to know these definitions for the rest of my talk. So there are two polytopes that are associated with submodular functions. Okay? And they're defined like this. It's a set of linear functions which, when evaluated on any subset of the ground set, are less than or equal to the value of this submodular function. Okay? So it looks kind of complicated. For this talk, we're just considering the optimization aspects. Okay? So what you need to know is that these polytopes generically have exponentially many facets. Okay? And that's pretty clear because they're defined by exponentially many linear inequalities. Right? One for every subset of the ground set. So you meet that. The base polytope has one additional equality constraint. Okay. So you can think of the submodular polytope as this dark gray area. The base polytope is some face of the submodular polytope. They generically have both exponentially many facets and exponentially many vertices. So imagine trying to solve an optimization problem that involves these submodular polytopes. It's a little bit scary, right? Because if you try writing this in, CDX or convex.jl or, standard modeling frameworks, how would you write them down? You'd have to at least either write down all the vertices or write down all the facets, right? How are you going to specify this polytope? Right? And as soon as you do that, your representation of the problem is exponentially large. Not good. Okay. One other piece of mathematics, so we can really start having fun. We're going to define the piecewise linear Lobash extension of the base polytope to be the maximum of linear functions over any point in the base polytope. Right? So given a vector x, we're going to take the maximum of w transpose x for w in the base polytope. Okay? So if you're familiar with convex analysis, right, this should remind you of Bechdel conjugates. Or the support function, right? It should remind you of duality. It should start like ringing duality parts of your brain. Okay. Okay. So the Lobash extension is the convex envelope of the original submodular function. And since many people have familiarity with using the L1 norm in order to convexify cardinality functions, right? If I really want to count how many elements of this vector are non-zero, instead I might use this convex realization of the L1 norm. Okay? The Lobash extension allows you to do similar transformations on arbitrary submodular functions. So, for example, if I want to count the number of subsets, Sj, that have a non-empty intersection with my set A. Right? I could do it using this function. If I want to convexify that, it looks like this, which is the Lobash extension of this submodular function. Okay, so it just provides machinery to translate between submodular functions and convex functions. Okay. And the Lobash extension is convex, which you can see just by the definition. It's maximum of linear functions. Okay. So here's the key. Is that linear optimization on the base polytope is easy. And this is an old result by Edmonds in 1970. I'm not going to prove it. If you stare at this formula, you'll figure out how to do it. But for us, what matters is that linear optimization on the base polytope is easy. Okay, so we can compute the Lobash extension, right? Because we can evaluate. We can perform linear optimization on the base polytope to evaluate the Lobash extension. And doing that actually gives you the W that maximizes this, and that means that we can also get subgradients of the Lobash extension. Okay, so these are going to be the operations that are easy in our universe, and we're going to be willing to build optimization algorithms out of them. So here's the primal problem we're going to consider. Get to the point. So suppose we want to minimize some smooth function g of x, a strongly convex function g of x, plus f of x, where f of x is the Lobash extension of a submodular function. So from all that previous stuff, we know these things are piecewise linear, they're homogeneous, they generically have exponentially many pieces, and subgradients are easy to compute. they take n log n time, but for us that's easy. Here's an application. Why would you care about doing this? So suppose that you want to denoise an image. You want to do background subtraction. You want to figure out what's in front of the image and what's sort of background. Imagine you're doing this for security camera footage. Someone's walking in front of the camera. If you try to find the person in front using the L1 norm, this is the reconstruction you get. It's very bad. If you use a structure norm that comes from the Lobash extension of a different submodular function, you can do substantially better. So they're kind of cool, but really we're here we're efficient optimization. I'm not going to tell you too much about that. So here was an algorithm that was proposed actually by the author of that previous paper, Francis Bach, to minimize functions of this form, to minimize g of x plus f of x. Okay. So here, just in that application, you should think of g of x as like a data fitting term, and f of x is like a regularizer. Kind of like, right, f of x, it generalizes the L1 norm, so you should think of it like a regularizer. So here's the algorithm. So he initialized an empty set of vertices, or you can initialize with any set of vertices you want. So at every iteration, you define an approximate function to be the max over w in that set of vertices of w transpose x. Okay? Right. So if the set of vertices were actually equal to the entire base polytope, right, then this would be f of x. Otherwise, it's an under approximation to it. We're going to solve the subproblem, minimizing g of x plus f hat of x. Okay. Now, this is just minimizing the strongly convex function plus a piecewise linear function with not too many pieces. So that you can plug into your favorite convex programming solver, no problem. We're going to compute a subgradient of the true Lobash extension, right, of the real function, at the current iterate, right, at the solution to the subproblem. We're going to add that subgradient to our set of vertices, and we're going to continue. So, as we add more and more of these subgradients, we start filling out more and more of the base polytope. So eventually we converge, right? There are only exponentially many vertices of the base polytope, so this definitely runs for no more than exponentially many iterations. That's not much, right? That could be a long time. Okay, so the set of vertices keeps growing. It gets big. For us, the memory is a problem because Moore's law is running out. And there's no known rate of convergence for this, so that was even worse. Okay, so we proposed a change to just one line of this algorithm. All we did is we said, well, instead of keeping the entire set of vertices that you used at the last iteration, we're just going to keep the set of vertices that are tight at the current iterate. And what we mean by that is that W transpose X is actually equal to F of X. Okay? So if you think of the Lobash extension as it's a piecewise linear function, right? So it's some piecewise linear function. It's defined something like this. If this is your current iterate X, right? It says if I were going to, if there's no point keeping this plane, right? It's not tied to my current iterate. I'll just keep these two. Got a picture of that. Yeah. Okay. This is a better picture of that. Okay. So here's how the method works. Let's imagine I'm at a current iterate x1, so here the black function is g plus f, and this blue function with the crosses is g plus my current approximation to f. Okay. So I look at the current point, right? The current point minimizes the current approximation. I look at the subgradient of the true function at that point. I add it to my approximation. So it makes the approximation tighter at the next iteration. So you can see the approximation is tighter. My next iterate minimizes the approximation. I look at the corresponding point on the original function. I add a subgradient to my approximation. Okay. Continue. Okay. I minimize this new approximation. This is my new point. I look up. I evaluate the subgradient at that point. But here's something interesting happens. So here, this part of the function, right? This part of the linear piece is not tight at the current iterate. So I'm going to drop it. Okay. And so you can see that my function approximation gets less tight at the next iteration. So there are two questions we should ask about this. One, how much memory does this use? Right? Have we actually solved the memory problem? How many of these linear subspaces could be tight at a given iterate. And number two, how fast does it converge? Does it converge? Right, it could even cycle, it could be really bad. So what we proved is that it has bounded memory, so the number of vertices that you keep track of is never more than n+1. It converges as long as G is strongly convex. And it actually converges linearly when G is both smooth and strongly convex. It's like basically as good as you can get in optimization. By the way, so in optimization, we're very modest. We use the word linear convergence to mean that the error goes down by a multiplicative constant at every iteration. So it looks linear on a semi-log plot, right? On a standard plot, it looks exponential, and if we were less modest, we might call it exponential convergence. It's pretty good. Okay. Interestingly, this also shows that the original simplicial method converges linear. So, pretty good. Okay, so here's the way to see it. And the way to see it is it uses a really pretty duality argument. Okay. So, look at the dual problem. The dual problem is minimize the Feinfeld conjugate of G over the base polytope. So, the conjugate of a strongly convex function is smooth. So this is the problem of minimizing a smooth function over a polytope. But it's polytope with exponentially many facets, so it's still a problem you should be a little bit scared of. Okay? But we know that linear optimization of the base polytope is easy. Okay? So what do we do if we want to minimize a linear function over a polytope for which base linear optimization is easy? Well, clearly we should use the conditional gradient method. Okay. So there are a lot of different conditional gradient methods. They're variants of the method I showed you earlier. Waystep, pairwise, fully corrective. All of these converge linearly as long as the function G is smooth and strongly convex. But the fully corrective Frank Wolfe variant has limited memory. In fact, you can show for another variant of these methods that you can get linear convergence with one gradient plus one linear optimization per iteration. But this method, the fully corrective Frank Wolfe, is particularly cool because it has a primal interpretation. So rather than running it as a dual algorithm, you can actually run it as a primal algorithm. And we'll actually see that it is equivalent to the limited memory Kelley's method that I showed you just earlier. So let's look at what, so I'm gonna skip this slide because it's only relevant to those other algorithms. So here's what fully corrective Frank Wolfe looks like. It's very similar. So we started a given iterate, W0, which happens to be a vertex. We look in the negative gradient direction. We take the vertex that maximizes the inner product with the negative gradient. We go in that direction, but here we do something different. We actually find the minimum of the function over the convex hull of V1 and V3. Okay? Next iteration, we take the negative gradient, we look in the negative gradient direction, maximize its inner product with the vertex. That vertex is V4. Next iteration, we find the minimum of the function over the convex hull of V1, V3, and V4. Okay, so this is a harder subproblem than you needed to solve for the standard conditional gradient method. But as long as the number of vertices isn't too large, it's not too bad. Okay, so here we are at W2. Let's suppose it's in the interior of the convex hull. Okay, it's in the interior of the convex hull, and we're on this convex hull is full dimensional. Okay, so if it's an optimization problem over R2 here, right, then this triangle is full dimensional. If it were over Rn, then we need a full dimensional convex set. Let's suppose that were true. What do we know about W2 in that case? Right, so here in this picture, what do we know about W2, right? It minimizes the function over the convex hull of V1, V3, and V4. We're done. Exactly. Why are we done?
Because the local optimum, then it's a global.
Yeah. So I mean, so it's definitely a local optimum over V1, V3, V4, right? And if we're to global optimum, well, the gradient has to be pointing in some direction from this, right? And if the gradient were pointing some direction, well, we would have just gone that direction, right? That's in our. Okay. So we have to be done. Okay. Otherwise, what happens, right? Otherwise, well, the optimum over that convex hull has to lie on a face, right? And so if the optimum lies on a face, where does the gradient have to be pointing? Out of the face, right? Otherwise, we would not be on the face. Okay, it has to be pointing out of the face. Okay. Now look at that gradient, right? This tells you that because we've got a convex function, this gradient actually provides a certificate that every point over here is worse than this point. Okay? Okay, so we don't need to consider any of those points ever again. So in particular, we're going to drop the vertex V3, right? Anything that you have to represent using V3 is suboptimal. Okay? We're going to look in the negative gradient direction. We're going to find V5, add it to the set, continue. Okay. So if the face was full dimensional, then at the next iteration, either we're done or we drop one vertex. Okay, so that limits the memory. This is the total algorithm. It's just exactly what I showed you on the last slide, so I'm not going to spend time on it. And so how much memory do we need, right? So we just need enough memory to be able to represent every vertex in a full dimensional set. Okay. So how many is that? Cartay-Dore tells us it's n+1 in R. If you don't know Cartay-Dore, then you should look it up because it's very beautiful. But I'm not going to explain it here. But it's exactly this argument that right, n+1 vertices makes a simplex that can be full dimensional. Finite convergence. So the active set changes at every iteration, and we never reuse an old vertex, right? Because we have this certificate that we always get better. So that means that we have to converge finitely, but they're exponentially many vertices, so that's not very impressive. We can actually show that it converges linearly for smooth and strongly convex objectives, and that's just using an argument that was already known for fully corrected Frank Wolfe. This is useful if linear optimization over the base polytope is hard, and so the convex problem is comparatively easy, right? If we care about not doing too many linear optimizations over the data. It's also kind of interesting, it's fine to solve the subproblem inexactly. So we don't need to have an oracle to exactly solve that problem. Actually, inexact solves don't do very much damage to the convergence rate. Compared to standard conditional gradient method, you might ask, is this much harder than running standard conditional gradient method? What does this buy me? I guess it's kind of interesting to compare. The memory cost is actually kind of similar. You might think the memory cost is more. For this fully corrected, we have to remember all these vertices, right? But if each vertex is simple, then comparing n simple things is comparable to just keeping around one vector, right? Which is your current iterate, where you are in the tool space. And it's also, interesting, right? If we have the function g, not the function g star, the Frank conjugate, it's not that much harder to solve this fully corrective subproblem than it is to just evaluate the Frank conjugate of g. So there's really not much of a hit to using fully corrected Frank Wolfe compared to the simpler sort of Frank Wolfe iterations. Okay, there's one more step to get to the really pretty duality. Okay, so this fully corrected Frank Wolfe subproblem, its dual has a subproblem back in the primal space, okay, which is just uses the same set of vertices, right? So it's minimizing u of x. Plus the maximum over w in that set of vertices at x transpose w. Okay. This is the same duality as you saw between the master problems, the primal and dual problems. This is the duality between the subproblems. Okay. So the first order optimality conditions between these two subproblems show that actually the active sets match. If I selected a certain set of planes that were tight in limited memories of Kelley's method, those would be the same as the set of vertices that I select in the dual method, fully corrected Frank. So that means that, in fact, like everything about these algorithms is the same. Like the sequence of iterates are the same, the objective values are the same, they're the same number of iterations, they use the same amount of memory. Okay. So because we know convergence properties for the dual algorithm, we also know the primal algorithm has exactly the same convergence properties. Proof by beautiful development. We have to think that. Sorry. Okay. So how does that actually work in practice? Let's take a look. So here's a simple simulated problem. We're going to generate a random function g of x that's smooth and strongly convex. We're going to make our little f the Lobash extension of this submodular function. It's a random setup. How does it work? So on a 10-dimensional problem, we can verify that, so this is the number of iterations, this is the number of vertices that we have to keep around. So we can verify that indeed the number of vertices is capped by 10 plus 1. Okay? And in fact, I mean, oftentimes you use substantially less than that. So there can be advantages even, even earlier, right? You can throw out vertices even before you get to this upper bound. You can see that on a larger problem. So when n equals 100, the red line is the number of vertices that would be used by the standard original simplicial method. The blue line is the number used by the limited memory Kelley's method. Here you can see that the, as I've been in the number of iterations, the original simplicial method in red, it converges a little bit faster as a function of number of iterations than our method. And that makes sense because it keeps around more information, it should do better. But if you look at it as a function of time, then the limited memory Kelley's method does better. Right? And that's because the subproblems are simpler to solve, especially later on, when they use many fewer vertices. Okay. So there's a nice advantage. Okay. Let me tell you about an even harder problem. No. First I should take questions, because this is the second part of the talk is not super related to the first. So interestingly, actually, we didn't notice the connection with duality until very late in the process of writing this paper. We were just analyzing the primal method, we were trying to prove it converged, we were trying to get some insight about how it worked. And it wasn't until we wanted a stopping condition. We wanted a stopping condition on the problem, and we wanted to tell which of these planes were tight and which of these planes were like a little bit loose. We said, right, well, if the value matches to within like 10 to the 5th, is it, right, 10 to the negative 5th, is it the same? Right, and what if it 10 to the negative 6th? Like, we weren't sure how tight it would have to be in order to converge. We were having trouble setting this parameter. And that's what motivated us to consider the duality theory. Right? We said, well, maybe the dual will have some insights. And when we looked at the dual, actually, everything was substantially simple. We had to rewrite the whole paper after submission. Any questions on this?
Right, I'll ask a naive question. Can you just pose a kind of problem that's on the borderline of how big a problem you can solve? Like a little bit explicit in terms of this list of constraints, list of objective functions, like how big a problem can you solve? What does it look like?
Yeah.
And probably I should have been able to understand that from watching your talk, but I didn't.
No. I think that's an important question. So so here's the way to think about it. Do you want the story for memory, or do you want the story for time?
Just give some guesstimate a problem that you think you could solve this kind of
Oh, you want, okay. So using this methodology, the hardest part is solving these subproblems. The subproblems involve n variable of n dimensions, and there are n constraints. And so I'm solving a convex problem with n variables and n constraints. The complexity is, if I want to use a fast method, it's going to be order n cubed. If my computer does 1 billion operations a second, right, then something on the order of n equals, right, 1,000 is going to take, tens of seconds. If n is 10,000, it's going to take tens of thousands of seconds. If n is...
Okay, so 10,000 what? So 10,000 is kind of the upper limit of, now just describe
10,000 dimensions.
And what is this?
I mean, I can wait longer, or I can use fancier optimization methods that converge slower and get
how's
less
the problem
good.
sound?
Yeah, so think about that. So in the imaging application, right, that would be the number of pixels in the image.
10,000 pixels.
So it's like a 100 by 100 image. It's
And
like,
what can you do with that?
so with 10,000, then you should be able to solve that in.
But so what does solve mean? What's the problem solve?
Solve means to do the background subtraction task.
And as a math problem, that sounds like what?
As a math problem, it sounds like minimizing g of x plus f of x. The problem was not very concrete because I wanted to get to the optimization part.
Okay.
The g of x, you should think about it as the model misfit. So how much does my my model of foreground plus background look like the original image? And the f of x, you should think of as how complicated is the foreground and background? Like how many times did a subject walk through the scene? Yeah.
So you have this idea of like dropping off vertices after you're able to, like draw the triangle,
Yes.
right?
Yes.
So I mean, like presumably, if like you didn't want to solve it for 10,000 seconds, like you could stop it earlier. Is there any kind of like guarantee on how far away from the actual solution?
Yes. Yes. Actually, so this is the nice thing about convex optimization is you get a guarantee at every iteration. In fact, you can get this straight from duality, right? So you saw the primal problem, you saw the dual problem, right? Yeah. You compute the value of the primal, the value of the dual. Look at the difference, and that's the bound on how far you are from the optimal value. And in fact, we'd recommend solving that problem using a primal dual method so that you can use the dual to decide which parts of the primal are tight. And so just as a side product, you get a bound on how far you are from the optimum. Yeah, so you might converge actually much faster, right? The numbers I was giving were sort of upper bounds.
I have just sort of a practical question to try to understand, how I would actually use this. So,
Yeah.
is it fair to say, so g of x is a logistic regression function. I want to do logistic regression,
Sure.
and I have 1,000 covariates, and
Yeah.
I have an L1 penalty on those
Yes.
covariates. The most naive thing I could do is just do coordinate descent, but each of those updates doesn't have
Yep.
a nice closed form solution, so that's annoying.
Yep.
So instead, you're saying you could do conditional gradient descent.
That's right.
But then that problem would be that if I had 1,000 covariates,
Yeah.
I would
Now,
go.
so the reason why this wouldn't be the smartest idea to do for logistic regression
Okay.
is that logistic regression. So in logistic regression, right, if the set that you're trying to optimize over is actually the L1 ball,
Yeah.
okay? How many facets does the L1 ball have? How many linear inequalities does it take to represent the L1 ball?
I'm not. So to back up.
Okay.
Instead of focusing on maybe why that's bad.
Question for other people in the room.
Well-
but actually, you only need twice as many as the number of dimensions.
Okay, but I
So-
guess
so-
to back up,
yeah.
ignoring that because I'm not
Okay.
an expert
So-
on
so-
that.
so-
But
yeah, yeah,
if
if
that's
we're
a
more
bad
complex, yeah.
example, then
Is it-
if that's a bad example, then is there a not contract good example? So you're saying this is not good for logistic regression,
Yeah.
but is there a
Yeah.
objective
So
function
the
I would
place where it's
actually
useful is where the submodular function that is forming your constraint set is a more complicated function.
Okay, so it's that the ball is the
Yeah,
the
where
L1
it's hard
constraint is-
to write it down explicitly, right?
Okay, so if I had an even weirder constraint.
Yeah, that's right.
Okay, but so anyway, to just back up to my example. So even if I had a crazier constraint,
Yeah.
I could still do coordinate descent. And then instead I could do this conditional coordinate descent, and the problem would be that maybe I could go for a really long time and have way more points in my vertex set
Yes.
than I even have dimensionality.
That's right.
Okay, and then you're saying that this could be better because I don't have to keep as many around.
That's right.
Okay, I understand it all. Thank you.
Okay, but right now, what I presented here is this is just mostly math. I actually think most of what there's a reason why my presentation here is mostly about math and not about the problems, because on this problem, I actually think the math is more interesting than the problems. I gave a camp talk 2 years ago where the problems were more interesting than the math. And there's been more work that I've been doing on that since then, but I didn't want to bore people who were here 2 years ago. Okay. But this is my talk where the math is more interesting than the problems. Let me tell you a little bit more about math that's more interesting than problems. Okay. Okay. So in the previous part, we saw that we could use less memory than maybe a naive algorithm would use. In this part of the talk, we're going to try to actually get optimal memory. Right? We're going to actually find the lower bound of the memory it takes to solve this problem, and we're going to solve it using about that much memory. Okay. So here we're going to parameterize the problem data. Is going to be, maybe it'll take n numbers to represent, or some multiple of that. The solution will take n numbers to represent, and we want to be able to solve this using as little memory as possible. The question is, can we get it down to n? Right? Definitely we need n to read in the data or write out the solution. Can we do it in n? In this part of the talk, here's the problem that we'll be considering. This is what I'm going to call a compact matrix optimization problem. So it's minimizing a smooth function f of a linear operator applied to x. Okay? So you can think of this as the linear operator is sort of measuring certain elements of x, or making certain, measuring certain linear functions of x. And we're going to do this subject to a constraint on the sum of the singular values of x, which I'm going to write as the Chapman 1 norm, S1. For this model to have a compact specification, what that means is the problem data uses order n storage. Problem data here is the linear operator a and the function f. For this to have a compact solution, it means that the rank of the solution is some constant r. Because I can write x using its factorization, and that will take me n times r numbers to write down. So, is the goal achievable for this class of problems? Well, here, right, I said the problem data is order n, the solution is order n. Okay. But just to write down the matrix variable, right, this is an n by n matrix variable. It takes n squared numbers to write down. Okay? So if I just write down the variable, I failed. Okay. I'm going to show you a method that is able to solve this problem using order n memory. Okay. For this problem, let me tell you about this application called phase retrieval, because this is one where maybe thinking about the scale of memory, it'll be sort of more relevant. So here, I'm imagining I've got a real object, right? And there are n, I've divided my object into n pixels, and I want to know how much stuff is in each of these pixels. I'm going to acquire noisy nonlinear measurements of the form, so I'm going to take the inner product of some vectors ai with x, x natural. I'm going to observe their absolute value squared plus some noise. And now this is actually a real model for microscopes. We've actually been working with people at the BioHub in San Francisco who are trying to make better and better and better microscopes. And this is how they model, this is what they think the microscopes really are doing. Okay. So we want to recover x. But we've got only the norm squared of the observation, right? We don't have the observation itself. This is a little problematic because we've lost some information, right, in the course of taking this norm squared. So we're going to do this trick. Okay. We're going to imagine there's some matrix x that's equal to x natural times its conjugate. And this norm squared, we're going to be able to rewrite using, and these are the very standard math, as a linear function, a trace linear function on the matrix x. We're going to try to recover the image by saying, I want the linear operator applied to this matrix x to match what I've seen b according to some loss function f. Maybe it's going to be a sum of squares of differences. And I'm going to add on these two constraints, and I'm hoping that these constraints are going to get me an x that's actually rank 1. Because if the solution is rank 1, then I can interpret it as the outer product of a vector with itself, and that outer product is the original thing I was trying to image. So here, right, actually we're in a similar regime, right? The n is the number of pixels in my image, right? So if I wanted like 1,000 by 1,000, if I wanted 100 pixels, if I wanted 1,000 pixels by 1,000 pixels, right? Then n is already 1,000,000. The dimension of x is 1,000,000 squared, right? This is actually not sounding good when my math memory is not growing. If I want to image more and more finely, I need more and more memory. storage bounds can be hoped for. We're going to assume that we access A, we access the problem data as A, right? Which entries do we observe? Using three operations, we're gonna look at A evaluated on a right quad matrix, and we're gonna look at sort of A conjugate in other combinations with vectors. Here, the input and output vectors are respectively in Rm, Rn, and Rd, right? We're sort of permuting them around. So we need M plus N plus D storage just to apply the linear map, right? To read in the data and write out the answer to the linear map. If the rank if we want to be able to output a rank our approximate solution, we need R times M plus N, for M rows and N columns in your matrix to write out that solution. So any algorithm is going to need at least B plus R times N plus N storage. We'll say the algorithm has optimal storage and it uses no more than that. Okay. So if we write down the variable, we've already failed. I'm going to skip all related work because we're running out of time. Okay. So this is what the conditional gradient method looks like for this problem, right? We would be minimizing our smooth function subject to a constraint on the Shackman-1 norm. Okay. And now this constraint, this is not actually a polytope, it's something much more horrible because it involves the singular values of x. Okay. But you can still picture this. It turns out the conditional gradient method is still easy to run because the minimum of a linear function over this constraint ball, you can actually find it just using the top eigenvector of the gradient. So it's given by the maximum singular vector of negative g. So it's easy to use the conditional gradient method. It's a fine idea. So this gives you the conditional gradient method for this problem, and this was already known. Our goal is to take this conditional gradient method and do it with optimal storage. So actually, this is a problem where you're going to stare at the algorithm, and let's see where are the places where we use more storage than we'd like to, right? Well, it's anywhere we see a big matrix. So that's x over here. It's this x over here. It's h over here, which is also a matrix. But those are the only places. It's all the x's and h's. Okay, so we're going to look at them and highlight them. Okay, so we're going to do two things, right? These are the two main ideas in this part of the talk. We're going to try to reduce the dimension of x. We're going to remove it from our problem and replace it with this low-dimensional dual variable ax. And then we're going to recover the solution from a randomized sketch. That part I'm really not going to be able to tell you about. But we're never going to write down x until it has converged to low rank. Okay? And here's the idea of how we do that in the algorithm. So we look for the places where x appears, and in every place that a big thing appears, it is pre-multiplied by a. So I'm going to introduce this dual variable, z, which is a times x, and I'm just going to drop x. Right? So I'm only going to represent and remember z instead of representing and remembering x. Okay. Z it's a much lower dimensional thing. It's in Rd, which we're assuming is proportional to n. And then now we've eliminated this big thing from our problem. Right? We're now solving the problem with optimal memory. This iteration actually produces exactly the same iterates, right? Because we've just done this like typographical replacement. But there's this weird thing where at the end, like you solve the problem, you find the final z, and you have the final z, but you don't have the final x. You have to figure out how to find the final x. Okay. So that's where sketching comes in. I'm not going to be able to tell you about this, but here's the idea: is we're looking for a low-rank matrix, and we can think of this low-rank matrix as an operator. Okay? A low-dimensional linear operator, like in order to figure out which one we have, all we need to know is how it operates on a low-dimensional subspace, right? Both how it operates sort of on sort of its row space and how it operates on its column space. And if we know that, we know the low-dimensional linear operator. Okay, so we're going to collect information as we run the algorithm about how this operator acts on its row and column space. At the end, we'll reconstruct the operator from its row and column space. That's the idea. I'm not going to tell you any of the math because we don't have time. Okay. Great. So how well does this work? I'm just going to tell you the answer in terms of pictures. Okay? So let's imagine this squiggly thing is the manifold of matrices of rank less than or equal to R. This is our initial iterate, and this is our final iterate. Okay? If the iterates of the conditional gradient method were moving like this, right? So you know that after R iterations, they might well have rank greater than R. If you add a rank 1 matrix at every iteration, okay? They're going to have rank greater than R, and slowly they'll converge down back to this manifold of rank less than or equal to R matrices. Okay. If the final iterate is on that manifold, our sketching method actually exactly recovers that iterate. Okay? So no problem. We actually got it. Okay? If the final iterate, we don't get quite to the manifold because we only solved the problem inexactly, then the point that we recovered can be no more than twice as far from the true final iterate as the closest point to the final iterate that's on this manifold of rank less than or equal to R matrices. It's pretty good. Okay, how does it work on phase retrieval? The answer is it does as you expect. It actually does have linear memory if you look closely on this plot. But I think more importantly, it actually works well. So this is a Fourier typography problem. This is a particularly challenging kind of microscopy problem where the measurements that you're able to take due to the geometric setup of this microscope are not very well conditioned. Okay. So if you try to do this using various of the non-convex methods that have been proposed, you get these like weird ringing artifacts, like just not recovering the image very well. You can see these. Okay. If you do this using the convex method, what you get, it looks a little bit fuzzy, but you can see the blood cells better without these weird artifacts. Okay. So, as expected, the convex method is a little bit more robust. It's a little slower, it's more robust, but what's interesting is that it's not using more memory than the non-convex methods. Okay. And here, these red boxes are marking the location of malaria samples. You can see are slightly brighter spots on these blood cells. You have to be able to resolve it fairly finely in order to spot the malaria. Cool. Okay, so I've just given you a very math-heavy talk. Thank you for bearing with me. I showed you 2 convex methods that get better storage than you might expect. Sketchy CGM got optimal storage using 2 kinds of new ideas. One is writing an algorithm using a smaller dual variable, and the other is to sketch and recover the decision variable. Whereas the first method I showed you gave a bounded storage algorithm using 2 very old ideas, duality plus the Pythagorean theorem. Thank you.
Any questions for Madeleine?
Yeah.
So this is more about like the application at the end, but
Yes.
you guys actually have to take what you see in the microscope and then run it through this processing.
Yes.
And then you get to look at it.
Yes.
There's no more like live microscope
There's no like,
to eye.
what do you see? So this is kind of interesting. So yeah, this is actually very subtle. So the thing that you see with the microscope, oftentimes these microscopes are designed in order to, so you're going to have several pieces of coherent light waves going through the sample that are going to interfere in such a way when they get out that the image that you see is going to look kind of nice. Okay, so it's like cleverly designed to look kind of nice. Okay, and that means, but the way that they do that is via these like clever interference things. It's not a quantitative methodology. What you're going to see, things that look like sort of shadows near edges or something like this. It's going to look okay as long as the length scales of the sample are not, chosen poorly with respect to the geometry of your microscope. But if you want to be able to resolve really small things or really big things, it can be problematic. And you can see this, you can construct images that fool these microscopes terribly. So where like the original image has a sort of radial periodicity of like 8, and the thing that you see comes out with a radial periodicity of like 16. Like totally wacky things can happen because of the fact that it's using one clever trick rather than actually trying to solve the problem. This is particularly difficult. I mean, when you think about imaging, you think about high school biology, right? Where you like stain your sample with purple so the organelles show up in purple, right? And then you look at it and you see the parts that are purple and the parts that aren't. So that purple kills the cell. So if you want to see the original cell, actually basically the whole thing is going to look clear. Okay, and the only difference is that certain parts, light is going to move more slowly in those parts compared to in other parts. And the way that that will show up is not any attenuation of the, right, so any attenuation of the light, like the light's going to be just as bright for all of it, but it's going to have a phase difference, okay, because the light went more slowly inside some parts than others. So the signal is all in the phase. You have to be more careful to recover that. So that's why in order to see it, you have to do some clever thing with cancellation, but you can see something small. So these are called, what they say is that these imaging methodologies are not quantitative, right? They produce pretty pictures, but you can't actually measure like how much cell is here compared to there. Maybe more biology people microscopy.
Other questions? All right. So there are refreshments next door. Let's thank Madeleine again.